All right, good afternoon, everybody. Looks like I hope everybody's enjoying this first week back to being able to go outside and not have to be stuck inside so much. I'm if you can't tell, I'm back in the office, so here I am. So yeah, so it's been very nice, right? Okay, so we finished that quiz. Oh, first thing I wanted to do before we get into any slide stuff. So I had a couple of you guys ask questions about this because I feel like this means that this probably is something I went over in, even though I went over it in the class, I didn't go over it well enough. And so I want to make sure this is clear about how this whole testing thing works. Okay, so what I'm going to go ahead and do is I'm going to share my code screen over here. All right. Oh, let me make it to where you can see that a little bit better. Come on. Okay. All right. So let's say that we have this method called sum that we're wanting to test, and we want to verify that the sum of 1 and 2 is 3. Okay. Now, the way that the method has been described in our instructions and our requirements is that it should take an integer a and an integer b, and it should return the sum of those two numbers. So it should add those two numbers together. Okay. All right. So here we go. So let's see. Yeah. So if I compile this, my test method, and run it, I get, yay, I have a passed test, right? So we are good, right? The method works, right? So we can say our method is working just fine, right? But the problem is if we go back over here and we look at the method itself, we see, oh, well, that's not right, is it? Well, you know what we should do? We should create a new test case to try to verify that that this actually works. Let's, instead of 1 and 2, let's do 0 and 3 and make sure that that works. Right? That this is a good test case, that this is a good method that returns the sum of these two numbers. So do this. Oh, wait. It's named the same thing. Let me just add that to it. Methods named the same thing. Okay. Now when I run it, now I get, hey, 2 passed test cases. Wait a second. Why did I get 2 passed test cases? I'm testing more than one thing, right? So what am I doing? And this has to do with what, when we are creating our test cases, we have to be smart about how we're testing. Notice that even though this is 2 different test cases, it still suffers the same problem, right? It still can pass if the value returned is a certain value. So when that question on the quiz asked for an example of code that would pass your test case but would not be correct, this would be something like what I'd be looking for, but for the assignment 2 stuff, not this. You don't write the sum thing in there because that has nothing to do with assignment 2, right? But this is why when we write test cases, we can't just rely on one test case for one method and feel like, okay, we're done, we've done tested it, right? We need to also be able to test for other things, because here's the thing. Now, if we say, okay, we'll create another test case sum 2, and we'll give it some other numbers. We'll give it 1 and 3 now, right? So now when we compile it and we run it, Oh, wait, sorry. 1 plus 3 doesn't equal 3, guys. Oops. Okay, here we go. And now when we run it, we should get, okay, now we get a failed test case. We expect 3 was what we get back from the sum, but we got 4 instead. Okay, that's a problem. So now what we would do is we'd say, oh, there must be something wrong with our code. Sure enough, it always returns 3. That's not what we're trying to do. So we can say that should be our sum. Compile that. We'll run that. And now we get all 3 test cases passed, right? So if we consider this is a correct solution to the method sum, right? This is an incorrect solution, but it still passed 2 of our 3 test cases, right? And this is why when we write our test cases, we have to be smart about how we write them to make sure that we are fully testing the system well. Now, does that mean that we have to test every possible input for A and every possible input for B and make sure that every possible output is, that those 2 put together would get? No, I'm not saying that. That's not what we do. We don't have the time. We don't have the space to be able to write that many test cases. We don't have the time to run that many test cases. But what I am saying is we do need to test enough that we can safely say we tested it well. We thoroughly executed the system to make sure that we got a good range of tests done. Okay. All right. So when the assignment quiz asked you to give an example test case, okay, so you did that. So you said this would be, so let's say it was just this sum thing here, the sum thing that we're talking about, okay? The thing you would have said for when I said write your test case here, you would have written like this here, this part here, okay? All right, this is my test case. Then when I said, okay, now write some code that would pass your test case but would not be a correct solution, this would be a good answer here. Okay, for something like that. I hope that what that meant was that you wrote code that you hadn't written before. I would hope that your code for assignment 2 passed your test case and was correct. I would hope that was the case. But it is possible for some of you that maybe you did pass your test cases and yet your code wasn't correct. I don't know. But hopefully what it meant was you had to think about, how could someone have written the method so that the test case passed, but it wasn't really a correct method? Okay, so it's just something for me to help you guys think about, because the truth is that in programming, there's lots of different ways to do stuff. There's not one right answer, right? We've talked about this many, many times. There's not one right answer to the problems that we face. There are many solutions to the problems that we're trying to solve. The thing is that some solutions are better than others, and some solutions are correct and others are not. Right, so this would be an example right here. This one over here would be an example of a solution that's not correct, but it definitely could pass some test cases. All right. Okay. All right. So let's get into data structures. All right. So I kind of gave a general label for this class's title being collections. And you'll see why when we get into the slides here. But for those of you who have looked ahead and you've looked into hash maps and sets, and stuff like that. That's where we're getting into now. Okay, we have already talked about some data structures already. The array is a data structure. The array list is a data structure. Basically, a data structure, and I mean, even technically, the object is a data structure. The data structure really is just about as a way to store connected things. Okay, and they could be connected by, they could go together as in, like if I had a student class that keeps, like for our assignment 2, where it keeps name, student ID, birth date, and you know, all kinds of other things that those aren't in our example, but those things those things are they go together because like your student ID along with your name and along with the courses that you take and all of that stuff, it kind of all packages together, right? And so that's why you could call it a data structure. But also some of the other data structures that we'll talk about how to store things that I say go together could be that it's like they are similarly typed things. So an array could be an array of integers. So it would be an array of the same type of thing kind of going together. All right, so let's just go ahead and get on into it. So basically a collection is just a container that holds a group. So now the array and the array list are the ones that we've talked about most so far already. Those are what we would call an ordered thing, which means you can get them by index value. So if I put something in the array at index 0, then something else in the array at index 1, and then something else in the array of index 2, they keep that order. They don't get all mixed up, right? It's not like, I'm sure I can find one. Like this, okay. So let's say, okay, let me see if you can see this. All right, so I have my bag here, okay? I have my bag, and I have a couple of notebooks, okay? And if I were to take my brown notebook and put it in my bag, take my other notebook with this Volkswagen Beetle, if you know who this is an old character called Herbie from some old movies, all right? Take that and put that in the bag. Now, they're not ordered in the sense that just because I put one in there first doesn't mean if I say get the thing out the bag, doesn't mean that's definitely the one that's going to come out, right? So a non-ordered collection, we'll talk about that. We'll refer to that as a set. A non-ordered collection, it just stuff's in the bag, stuff's in there. It doesn't matter. There's no order to it, right? So you can't really sort it. You can't do much in terms of comparison of one item to another to keep them in some kind of sorting or ordering or anything like that. However, lists, arrays, those are all ordered collections, okay, which means that if something is in the first position, it stays in the first position. If something is in the second position, it stays in the second position. And I always know where to find it, okay? All right, so is there anything else I wanted to say about that before moving on? And we'll talk about some different ways of how lists and sets and maps can be made, okay? Because the array, and I'm really kind of thinking to myself, I really wish I had my tablet because I would love to draw some of this stuff. I need a whiteboard, right? But it doesn't work. Okay, so so maybe I'll hold off till next week some of the stuff that I want to draw, so I can draw it there and bring the tablet with me then. Okay, so the lists are ordered, the sets are not. Okay, and maps, it's kind of a mixture of the two, but really maps are unordered as well because of the keys that they use, but we'll talk about all that. Okay, but a collection is the general term that we use for all of these things. Okay, so let's talk about, okay, so this is a big UML diagram, but you should be able to understand most of it. So the idea here is that the collection is kind of the parent interface that kind of says this is what everything kind of inherits from that, or implements. Everything kind of implements collection. Everything down the line here. Okay. There are sets, right? And we'll talk about maps later. Maps will be the next set of slides, right? But there are sets, there are lists, right? There are queues. We'll talk about what's a queue and what's the difference between a queue and some of these other things as well, all right? But a queue is another example of an ordered arrangement, an ordered collection. Okay. So then you have the list gets us down to this thing right here, this array list. Now we've talked about array lists before, you've used them before. They're a perfectly fine data structure that we can use. Basically, the kind of underlying implementation of, of an array list is an array. It's kind of like a dynamic array. But there are some methods that array lists get added, there are methods that the array list class implements to make things a little bit easier on us. Remember, one of the things that we talked about before was if you had just an array structure and you tried to insert an element somewhere inside of the array, the problem would be that you'd have to take everything after that element and you'd have to move it over. So move this over here, move this over here, move this over here, finally get the guy in there. Finally get that in there. Okay. An array list does that for us. Now it does all that work. It moves everything over because its underlying data structure is an array. And so it will have to move all that stuff over, but it does that stuff for us. So that we don't have to, write code that does that. We simply say, I want to insert this value in this position. And what does it do? Moves all that stuff over, puts that guy in there. Okay. A linked list, we'll also talk about that because that'll be a new type of list that we'll introduce. A linked list. Hello? Okay. A linked list is a little bit different than an array list. It's quite a bit different in that it's not consecutive memory location. See, the array list was consecutive, or what we called contiguous memory locations. All right, but a linked list is not set up like that. A linked list has a head pointer and then a head node, and then that node has a pointer to the next node in the list. Okay. And I'll show you, we'll show you kind of some visual stuff with that one. Okay. Okay. So again, these are some of the methods that are in a collection. Notice this add, right? Add a value to our collection. We had that in the array list, right? Contains, we had that in the array list. So all of these are methods that the array list, right? Which the array list extends abstract list, which implements list, which implements collection, right? And so the array list has this method called contains, right? Equals, is empty, remove, size, right? So all of these are methods that we've talked about for the array list. And then where does it get them from? It gets all these methods from the collection interface that it inherits. Right. Okay. You'll also see some of this has next and next, the iterator, right? An iterable collection, right? So that we could move through them, right? Move through all the objects in our collection. Okay. Right. So we will talk about the list interface. Again, the list stores elements in sequential order. There is an ordering to this. We can get an element from from an index. All right. So this is just like the array list. Okay. So we have an interface called list that implements the collection interface. Okay. So I've been saying all along, this whole, what's the difference between an array list and a linked list, right? Now, an array list, like I said, its underlying data structure is an array, right? But an array is, an array is fixed once it's created, but an array list can grow. The problem with an array list, right? An array list is that it can't grow, it can't shrink, right? An array list, once it has so many positions available to it, it's stuck. It cannot shrink down from there. It can grow. We can always add more array list positions, but it does not shrink. Like if we find ourselves with 100 positions of an array list because we've put 100 items in there at some point, and then now we only have like 2 or 3, and we'd like to shrink it. We can't do it without creating a new object to make that happen. Okay. All right. So because of the way that these two structures are implemented, an array list, if we need to get to an item at a particular index very quickly, if we need to access to get the information, get whatever the object is from a particular index, and we need to do it quickly, the array list is going to be the most efficient option. And that's because, again, the array list, its underlying data structure is an array. An array is a set of contiguous memory locations. Okay. Contiguous meaning the thing at the 0 index is at a certain position in memory. The thing at the 1 index is at the next position in memory. The thing at the 2 position is in the next position in memory, and so forth. Okay. So if we want to get to something very quickly, it's simply a matter of adding the amount of memory addresses, going to that next thing, done, we're done. We can grab it. Okay. So if we need to get to something quickly through an index, an array list is very efficient. But what about if we need to insert or delete things from our list? An array list, I'm gonna pull up the whiteboard because I need you guys to see this. Okay. An array list does not do that quickly, insert and delete, because of the way that it is set up. Because remember what we just said was, if I need to insert something into the array list, it moves all the other things forward and then puts my guy there, puts my thing there, right? Well, yeah, we don't have to write code to do that, but the array list method does do that for us. It moves all those things forward and then puts our thing in there. Right? So it does all that stuff for us, but it's still having to go through that whole process. Right? A linked list is much better for inserting and deleting. And let me go ahead and what are you doing? What is this? No. I don't want to be. No. I can't do whiteboard on here now. Must have been connected with a different account. All right. I'm sorry for that little tease that it was going to happen, but I guess it's not going to happen. All right, which means what we'll do is I will go through this set of slides, and what I'll do is I'll go ahead and kind of run through this set of slides, run through whatever I can of the next set of slides, and we will do drawing stuff. I'll do drawing stuff on the tablet next week because I really think it's good for you to be able to see it. Okay, all right. So I have an array list, and notice that it implements the list interface. Linked list also implements the list interface. Okay, but if you go back, if we go back to 6, that's right here, right? We'll see that the linked list can kind of, it gets parts of it from multiple different places, right? It inherits from this abstract sequential list that extends from this abstract list, which array list does as well. But then linked list also gets this whole, DQ thing as well. This is not as important. The main thing to understand is that both of these linked list and array list, this should not be seen that the linked list is a queue in and of itself. What it is, though, what you'll see hopefully here, hopefully today, maybe next week, is that a linked list is a really good data structure for making a queue happen. Okay, a queue is a data structure where first in, first out. It's often referred to as FIFO, first in, first out. Meaning that when the first, it's kind of like the queue. If you're British, you use the word queue, British English, at the grocery store. That when you walk up to the, let's call it what, the till, we call it the register or the kassa or whatever you want to call it. Right? You walk up to check out, to buy your groceries, and the first person that comes to the till, to the checkout place, right, they are going to be the first ones that are served. And then if someone comes in behind them while they're still getting served, and someone comes in behind them and someone comes in behind them, right, the person at the register doesn't say, hey, you third in line, I want to serve you now. They don't just randomly choose somebody, right? It's always first in, first out, first in, first out, right? Right. Well, that's how it's supposed to be. But if you've been at Negros or A101, you kind of know sometimes it doesn't always work out that way. But that's how a queue in data structures works, is it's always first in, first out. There's another type of data structure that you've probably heard about, and I think we may have mentioned it once. It's called the stack. It's the opposite. It's called LIFO, last in, first out, and it's like a stack of product. It's like a stack of books or pancakes or whatever. And you put one thing, you can see me, okay? Put one thing on top of another, and then on top of that, right? And then whatever was the last in is going to be the first thing that we pull off the stack. Okay, last in, we pull that off the stack, and so forth. Okay, so that's how a stack works. As a stack is what we call it LIFO, last in, first out. So if it's the last on top of the stack, then it's going to be the first one that we grab off of there. Okay. Grocery stores don't operate like that, right? It's not like, oh, that guy came last to the register, we're going to take him first. No, no one would continue to go to that grocery store. All right, but a linked list makes for a really good data structure. Actually, it makes for a really good data structure, as you'll see when I draw this stuff out. It makes for a really good data structure for both stacks and queues, just slightly different ways that we do them. Hold on a second. Okay. We can look to some examples of how we can do an array list and a linked list. Right. We can create an array list from an array. We can create a linked list from an array. Okay. We'll take a look at this example where we have an array list of integers where we can add things at a particular index. What I really like about doing this example with you guys is I'm going to show it to you visually on what's called the canvas on JGrasp, so you can see kind of how that works. Okay. All right. So we'll see how this works, right? And notice that here we can even take a list that's of a certain type, an integer array list, right? We can add all of our integers to it. Then we can take that array list and use it as a passed parameter to the creation of a linked list that's of an object type. So now, instead of having just integers in here, integers in this linked list, we could add other things as well. And we'll see we have this set of integers that are these numbers here, right? Display the linked list forward. Now we've added, right? We've added two things that were not integers. Why? Because the linked list is an object type list. Okay. And then we can iterate through going both frontwards and backwards. Okay. All right. We also have talked about this whole the array list before. We looked at that example before. Now, we had talked about comparable, right? We had talked about the comparable, but now we're going to talk about a slightly different way to compare two things. Because remember that what we needed to do in order to compare two objects was they needed to be instances of comparable. Right? We had to have them implement the comparable interface. Right? But now, but what if we don't want to force our programmer to have to make something an instance of comparable, but we do want to compare the elements of different types? Okay, we can do that using a comparator. We can define a comparator to compare two elements, right? And then the comparator interface will do the same thing as that, what we talked about before about the compare to, right? In the comparable interface, the compare to method, where it's provided a negative value if the first item was less, it provided a positive value if the first item was more, was greater, whatever that is, and it would provide, and it said 0, return to 0 if the two elements were effectively equal. Okay. The comparator, on the other hand, the comparator interface is something that we can create so that the class that we're writing doesn't have to implement an interface in order for it to be comparable. And I'll show you an example with this, okay? I'll show you an example. So this geometric object comparator is one that we can use here. So notice that here we don't change the geometric object. All right, where are you? Guess it's not in here. Okay, we didn't make the geometric object class comparable. We did not have it implement the comparable interface. Right? Instead, what we did was we created this comparator that uses the geometric object class to compare the two to each other. So here, remember, if area is less than area, we return a negative number. If the areas are equal, we return 0. Otherwise, we return 1, meaning area 1 must be greater than area 2. Now, whenever we want to use something to determine which one is the maximum between two objects, we have to also send this comparator as well. And we just say, you know, create this new geometric object comparator. Okay, so there's a trade-off here, because one thing I said was, in doing it this way, we don't have to have geometric object itself be an instance of the comparable interface. Okay, so we don't have to change the geometric object class. Okay. But we don't have to change the geometric object class, but we still want to compare two things. We still want to compare two geometric objects for the purposes of sorting, for the purposes of determining which one's greater than that, for, I don't know, maybe in a new assignment 4 that says that you have to make the semesters happen in order, right? You might want to compare two things, but you might not want to make the class, like in this case, the geometric object class, you might not want to make it an instance of comparable. Well, what you can do is you can create this comparator instead. Okay, and then use it to be able to compare two objects. Okay, so let's see, let's got a few more minutes. Let's keep on. Talk about a few of the methods that the collections class has. So some of the collections class, notice that, let's see. If we have a list type, we can sort it. We could sort, if we get past a list to this method, I think the list would have to be instances of comparable in order to do this. We could also use a comparator in order to sort the list. So if we don't want to make the items in the list be instances of comparable, we could use the comparator instead. Max, min, right? All right. So some of these things are for ordered list type structures. Some of these methods are for any type of collection. Okay. All right. I'm not going to talk about the vector class. All right. I do want to mention the stack again. What we talked about was the LIFO, last in, first out. Things that go to the top of the stack come off first, so last in, first out. Right. Pop is what we do to get the top element off of the stack. Notice that it returns whatever the stack is holding. So whatever type of object the stack is holding, that's what it's going to return, because it's taking that top element and popping it off, taking it off. Push puts a new element to the top of the stack. Right? Peek is not something we do a lot of, but it is something where we can say, look at what the top element of the stack is, but don't take it off of the stack. Okay. All right. A queue is a first in, first out, a FIFO data structure. I talked about this, about like if you're at Migros or A101, first in, first out, first in, first out. That's how it should be, right? Like I said, I've been a part of those things enough in grocery stores, not just here in Turkey either. It's all over the world. People like, oh, I just have this one thing. I just have this one bottle of milk I need to buy, and you have a whole basket. So can I go first? Which is why priority queues are important. Okay. Now, a priority queue, right? In a priority queue, elements are assigned priorities. So a queue is always first in, first out. But let's say that you are at the hospital and you come in, you would think, okay, whoever comes to the emergency room or whatever it is, whoever comes first should get served first. Right? So if you come in and you say, hey, I think I broke my hand, or I think I broke my arm, and I need the doctor to look at it, or I've brought my son into the hospital before because he fell and really hurt his chin and he was bleeding everywhere. Bring him in. Can the doctor look at him? Yep. Okay. Well, but we're looking at this other child first. You'll need to wait. Whatever. Right. Okay. So that's how it should work, right? First in, first out. But what happens if someone comes in and they say, "Hey, I got a paper cut." Okay, like a little paper cut, piece of paper, cut my finger. And they say, "Okay, well, you'll have to wait. You wait your turn, and you sit down and wait." And then it gets to be their turn. And they're next. They're like the next time, the next doctor that becomes available, they're gonna see this person with the paper cut. And right at that moment, somebody comes in and says, "Oh, I fell and broke my leg," and it's like their ankle is maybe like twisted all the wrong way or something like that. I need to see the doctor. And you say, "But no. You have to wait your turn. I have a paper cut. You have to wait your turn because we're in a queue. We're in a queue here. So my paper cut, I was here first, right?" I would imagine you would agree. Most doctors would say, your paper cut can wait. I am going to see this person with the broken leg right now, right? I think we would all agree that that would be the best way to handle that situation. And that's what a priority queue is all about. A priority queue is all about saying, this person, this item in the queue should have a higher priority because it's more important. Okay, it's more important that we service it right now. Okay, so the broken leg gets a higher priority. The paper cut gets a lower priority. So even though the paper cut came in first, the broken leg gets serviced first. All right. Okay. Hope you guys all agree with that. I'm assuming you would agree with that. All right. So we'll do this real quick and then we'll take our break. Some methods of the queue interface would be to offer. Sometimes this is called enqueue, E-N-Q-U-E-U-E, right? But we take an element and we put it into the queue at the end. So it gets put into the queue, all right? Poll, right, would take the first takes the first element, right, from the queue. So it just services the next thing, whatever that is. Sometimes this is oftentimes this is referred to as DQ, D-E-Q-U-E-U-E, DQ. Okay. Remove is kind of the same thing, but it just throws an exception if the queue is empty. Poll gives us a null if the queue is empty. And peek does the same thing as on the stack. Okay. All right. So we'll go ahead and take our break here. I think we might be actually done with this set of slides from everything that I wanted to go over for that. Let's make sure. Yeah, what I'll do is I will, yeah, we'll be done with the this set of slides then today. And what we'll do is I'll show some examples when we come back from our break, and then we will end our class actually early. Since you guys had that quiz today, we'll end our class early at 3:30 today, or 3:20 today. Okay, all right. So let's take our break, 10 minutes, and I'll see you at 2:32.